Hey, this is Dr. B, and here's an introduction to electrochemistry. Consider the reaction between zinc and copper sulfate. That will form zinc sulfate and copper. We call this a redox reaction. The zinc is losing 2 electrons to form zinc 2+. The copper, which is already 2+, is gaining those 2 electrons to plate out pure copper. So when you do this reaction, you will see a copper precipitate form. It was discovered in the early 1800s that you can take the two half reactions, that is the oxidation of zinc and the reduction of copper 2+, and separate them using a wire and a salt bridge. We call this a battery. And here's what it looks like. The zinc, which is being oxidized, is placed in one beaker inside a solution of zinc sulfate. And the copper 2+, which is getting oxidized, is placed in another beaker. I'm using a copper cathode. The cathode is where the reduction occurs. And this should work, right? Zinc will naturally lose its electrons spontaneously. They'll travel through a wire, and as they do that, they produce an electromotive force, enough to perhaps light a light bulb. And they will go through this copper cathode right into the solution where those electrons can attach to copper 2+, and it will plate out copper right on that cathode, that piece of metal there. And this works fine, but you should also consider that we need to maintain ionic neutrality. In other words, if this was all that would happen, you'd have a plus charge here and a minus charge there. This is offset by the use of a salt bridge. In other words, the zinc 2+ that enters this solution can gain electrons. You just have a salty paper towel or some other method to provide ionic neutrality. And those zinc ions will then attach to chloride ions here. And the potassium ions will enter solution here because we have copper sulfate that lost its copper. So you have some naked sulfate ions looking for something positive, enter the potassium ions, and you maintained ionic neutrality. And this cycle is known as an electrochemical cell. They call this one a galvanic cell. And it will generate electromotive force. It will generate some cell voltage, 1.10 volts. What's happening is the zinc is getting oxidized, the copper is getting reduced, the salts are being transferred, but they're just spectators, so that's just the net reaction. It doesn't really matter what those spectator ions are. Notice here we didn't bother using sulfate. We just used any salt because that can work just fine. So it's referred to either the voltage or the electromotive force or the cell potential. And we can write it out using cell notation. There's our oxidation. There's our reduction right there, the copper 2+. Let's assume that they're both 1 molar in solution. We can write a cell diagram. There's the anode side, there's the cathode side. Anox, cat red. Oxidation for the anode, reduction for the cathode. We separate these by a single line for the phase boundaries, right? That would be the zinc turning into the zinc 2+, going from solid to aqueous in both cases. Here, aqueous to solid. And we have a salt bridge here that shows that we have to have the counter ions being transferred in order for this to work out. This is an introduction to electrochemistry.